Thank you for tuning in to the HACARUS webinar series. The HACARUS marketing team has the pleasure to present this webinar to you on behalf of HACARUS data scientist Ryuji Masui. Today's topic will be on hyperspectral imaging, or HSI for short. We will cover what is it, how does it work, and what are we doing with HSI and AI. First, to briefly introduce today's author, Ryuji Masui. Ryuji is a data scientist here at HACARUS, and his recent activities and contributions to the tech community are widespread. Not only is he a member of our explainable AI team, he is also contributing to the development of the core algorithm for Spectro, HACARUS's flagship visual inspection solution. He has also recently been focused on AI thought leadership, writing articles for CodeZine and Ledge AI, as well as giving lectures at Shiga University, one of HACARUS's academic advisors. Also, just to let you know, he will be giving a webinar using Zoom on the 22nd of July 2020, so please feel free to tune in if you are interested in the topic Features and Applications of Sparse Modeling Techniques. Note, this will be a webinar in Japanese. Next, I will now briefly introduce HACARUS. We are the leading provider of explainable, lightweight AI tools backed by Miyako Capital of Kyoto University, among others. Our solutions are primarily used in the medical, manufacturing, and industrial space to enable humans to make better, faster, and more reliable decisions based on AI-driven insights. HACARUS's proprietary AI engine is built using sparse modeling, an AI method that understands data like a human would and provides clear explainability. Our AI is non-deep learning based, which is capable of learning and inferring on edge devices. To learn more, please visit our homepage, hacarus.com. The topic of today's webinar is hyperspectral imaging, HSI, and how we apply HACARUS AI to this field. Let's get started. First of all, what is HSI? Hyperspectral imaging is a method of capturing reflected light from an object with high resolution in terms of wavelength. Compared to a conventional RGB camera, where only three channels are captured, red, green, and blue, HSI-enabled camera can distinguish 200 to 400 wavelength channels, allowing for far more complex images. So, why is this technology attracting attention? In a nutshell, the reason is that hyperspectral images have rich information in terms of wavelengths. In the image at the bottom right, taken by an HSI camera, you can see that the image has 3 dimensions of data. HSI images allow us to distinguish between objects that were not distinguishable with conventional RGB, such as the differences between salt, sugar, and flour, and also different metal plates where conventional RGB cameras and the human eye could not identify such differences. HSI is useful for use cases such as crop identification, where what is grown can be identified from an image from the sky, and food production inspections, where you can find if anything is mixed in by mistake. Another use case is material inspections, where you can identify the difference between similar materials in order to detect anomalies. However, HSI has restrictions. One camera today costs between $1,000 and $30,000 US, which is making it difficult for this technology to be widely adopted. Moving on, we will now take a look into hyperspectral imaging and how we are applying our AI to it at HACARUS. The reason we looked into this technology was that a recent paper was published on the topic of how sparse modeling can enhance the capabilities of HSI. At HACARUS, we decided to do a reproduction of the experiment presented to analyze the potential integration of sparse modeling into HSI, and in this case, the focus was on classification of crops based on HSI images taken from above a farm. In detail, we performed an accuracy comparison of the conventional support vector machine (SVM) approach, which is a conventional AI model, and sparse modeling. The data is 145 times 145 in size and has 244 wavelengths. We created an AI model to identify such wavelengths and successfully predict where each crop is farmed. The image on the far left is what the farm actually looks like, which both models are aiming to predict. Initially, the training data is made from the true data, which will be then used to train both AI models. The two images on the right are the results. The image labelled SVM is the result where the conventional SVM model was used, and the image on the far right was the prediction using sparse modeling. You may be able to tell the difference just comparing the images, but the accuracy score tells the same story. That is to say, the conventional SVM resulted in an accuracy of 80.188%, in comparison to sparse modeling, resulting in an accuracy score of over 96%, which is significantly higher. In conclusion, we were able to confirm that sparse modeling indeed did increase the performance of HSI as said in the published paper. As a next step, we wanted to take HSI further with our own experiment. With the benefits of sparse modeling for HSI confirmed in the initial experiment, we decided to design a new experiment to find out if sparse modeling extracts core features when combined with HSI. The experiment in detail was unsupervised semantic segmentation to see if it's possible to divide data into semantic regions. That is to say, whether this model could identify meaning. The image on the bottom left is a simple one with 5 oranges, and if we perform semantic segmentation on this image, the result on the bottom right was returned. The semantic segmentation was able to identify and segment the wall, the 5 oranges, and the floor. So, what happens when we use sparse modeling in semantic segmentation? This slide here shows the results. From this result, I believe you can see that the oranges, the wall, and the floor are somewhat segmented. However, can you see that the orange on the top left is not successfully segmented as an orange? It seems to be classified as some other thing. Why was the orange on the top left not classified as one? This actually is due to the fact that the orange in question is in fact not an orange fruit, it's an orange ball. With RGB, it's hard to determine that the orange in the top left corner is fake. It cannot differentiate actual oranges and orange balls. But with HSI, we can successfully identify the difference without any training data. As the experiment results show, we have confirmed that sparse modeling can extract essential features using HSI. Finally, I will briefly cover future prospects of HSI and HACARUS AI. Firstly, as we provide a visual inspection solution, Spectro, we will continue to develop anomaly detection algorithms using HSI. This is to be developed based on the Spectro algorithm, and the performance will be evaluated with actual data as we aim to launch this as part of our solution to support further visual inspection use cases. Secondly, high-speed imaging of HSI with software will be explored. HSI has potential demand in food inspections in factories. However, some inspections, such as flour inspections, result in blurry images due to high-speed flowing of the food. This hardware issue is preventing HSI from fulfilling its potential in this field. So, instead of waiting for the hardware to evolve, why not try to solve this issue with software? We will certainly continue our efforts. Finally, an ongoing investigation of the potential applications of HSI is being done in a number of areas. For example, we could estimate depth from the blur of each wavelength, and also use HSI to identify issues that RGB or the human eye cannot see. Thank you for tuning in and learning more about HSI and AI. If you are interested in learning more about HACARUS, please visit our website, hacarus.com. We look forward to providing more content in the near future.